We've been talking about thermodynamics part 2. So we talked about entropy, which is the disorder, craziness, randomness. I'll spit that out maybe. That is delta S. And remember, when things get more crazy, it gets more positive, and when things get more ordered, it gets more negative. And we can use entropy to help us determine whether or not a reaction is spontaneous by calculating the delta S of, they say, the universe. Sounds official. And that is the delta S of the system plus delta S of the surroundings. And remember that we can use delta S of the system to help us understand whether or not we are increasing or decreasing the order. It will not necessarily tell us if the reaction is spontaneous or not. That is what the delta S of the universe. So our delta S of our system is basically our delta S of our products minus the delta S of our reactants. And this is usually table values that you look up. And we do calculate just like we calculate delta H and delta G and all those guys. We want to multiply by the coefficients in the balanced equations by the figures that you find in there. Remember that you can make a fairly good prediction about order or disorder that's happening in an equation, especially if there's gas molecules involved. So if you have a reaction that produces more gas molecules than it started with, then the amount of disorder is going to increase and the amount of entropy should increase. And we should end up with more of a positive delta S value for the reaction. If you actually end up with a product side there that has less gas molecules than you started with, then you're creating more order and the entropy should decrease and you should end up with a negative value for delta S of the system. Remember that the delta S of surroundings is related to the delta H or the enthalpy of the reaction and the temperature, and they have this sort of opposite relationship. As we talked about, the delta H is a negative value if it is a exothermic reaction, and that would be the system giving off energy to the surroundings, and that energy would be absorbed by the surroundings, creating a lot more disorder, and we would end up seeing a positive value for the surroundings. And that's really why the negative is here, negative for our delta H, negative there, turns our delta S into a positive number for the surroundings. Again, the temperature here does need to be in Kelvin, so everything's all good. If we have an endothermic reaction, then we're going to absorb energy from the surroundings. That's going to really kind of slow everybody down in the surroundings. Everybody's not flying around craziness, right? They're kind of slowing down, and that's going to create a lot more order that's going to happen. That would be a positive value for delta H, along with a negative would turn our delta S for our surroundings into a negative value, which would imply that it is increasing in order. We also talked about the idea that temperature of the surroundings does play a factor in terms of how much craziness or non-craziness you may see, depending on the reaction. Again, if our surrounding temperature is relatively high to begin with, the amount of energy coming off of the delta H is probably not going to add that much more entropy to the surroundings. So again, that temperature does play a role. Again, if you add these together and you calculate the delta S of the universe and you end up with a positive value for the universe, that means the reaction is going to be spontaneous the way it is written. As we've been talking about, again, a reminder that when we talk about spontaneity, we are not talking about fast or slow. We're just talking about under those conditions, we would expect this reaction to take place. Again, it could be really fast, could be really slow, could be somewhere in between. But then that is what we're talking about when we talk about spontaneity. We then got into delta G, which is Gibbs free energy. And the free energy is pretty much what it sounds like. It's available to do some type of work. And we can actually use delta G to figure out whether or not a reaction is spontaneous or not. There's a few different sort of delta G equations we'll see. I think we saw a couple up front. We could calculate the delta G by taking delta H minus T delta S. And again, this is our free energy. This is our enthalpy. This is our temperature in Kelvin, and that is our entropy. Remember, as we talked about last time, you do have some unit issues here. That's going to be in kilojoules in most cases. Delta S is usually in joules. Thank you. And you do need to do some type of conversion, obviously, if you're using this equation. Otherwise, you will obviously get the wrong answer because you'll be about 1,000-fold off there. Another way to calculate the delta G, you can calculate the delta G by taking the delta G of the products minus delta G of the reactants, like pretty much all other thermodynamic values. You can look up the delta G of what's known as delta G of formation, and you can again find the correct state, the correct things, and multiply obviously the coefficients just like you do with H, S, and G in this particular case. And the deal with delta G is if you got delta G that is negative, then the reaction should be spontaneous the way it's written. That means it should kind of proceed from reactants to products. If you got the delta G and it's positive, it's going to be non-spontaneous the way it's written. If you actually reverse the reaction, it'll become spontaneous in the opposite direction. And if you have delta G is equal to 0, that is going to be at equilibrium in this particular case. Now, like I said, there's a couple or a few different delta G sort of formulas. And again, people sometimes ask, when should you use which one? I would always recommend just kind of using based on what is given to you. So if they actually give you an H and an S in a problem, then use the guy on the top right there. If they just give you an equation, that's it, then go to the table and do products minus reactants. And again, that's usually the best sort of approach there. Any questions on any of that there? Yeah.
So for the delta S to represent entropy, how is that different from the delta S of the universe system?
The delta S in this case is actually the delta S of the reaction or the system. So that's the one typically that we're using here, along with that's the delta H of the reaction. So as we are mostly interested in the system or the reaction we're dealing with, those are usually the values that we use here. And that's why we can look at delta G to help us figure out spontaneity, as it kind of just focuses on the reaction and what's going on in the case. So all those values are from the reaction. That's not the delta S of the universe right now. Other questions? Okay. So let us continue on this journey of fixing. Good chart. I like it. Let me figure out what's going on. No, I'm just kidding. All right. So in thermodynamics, you oftentimes are asked questions. A lot of times, they will ask you sort of, what do you think is going to happen? And they really won't give you numbers, but they'll tell you something like, hey, this is positive and this is negative at like normal temperature. So we could actually use this equation here that we solved to help us make some predictions of what should happen in terms of spontaneity. So let me just, since we got 4 boxes there, let me rewrite this 4 times and we'll talk about each of the deals here. I'll put one over here. And one for good measure over here. Why not? On a slight angle there. There we go. And it kind of looks like an A. All right. So in this case, we want to think about a couple of things. As we mentioned before, we have delta H here, which is in kilojoules, and we have our delta S, which is in joules. And if we have, for example, this first box right here, our delta H is going to be endothermic, which means that this guy here is going to be positive. And our delta S is going to be increasing, which means the delta S here is also going to be positive. So the only way for delta G to be negative and become spontaneous is we would actually need it to have a very high temperature in this case. So temperature is kind of the important factor. And that is because, again, this guy's at joules, this guy's at kilojoules. So he's got like a 1,000-fold jump kind of on the back end. So the only way to make this back end, which is minus here, larger than the front end of the equation, is we would need our temperature to be a very high temperature in this case. So under this conditions where you have a delta H that's positive and delta S that's positive, you would need a really high temperature usually for the reaction to be spontaneous. At low temperatures, this back part is not going to be large enough to overtake the front part, the delta H part, and you're going to end up with a positive value for delta G, which means it would be non-spontaneous at low temperatures. Now, if we go to the box over here, and here we then have a exothermic delta H, which means this guy is going to be negative, and we still have a positive delta S, which is over here. And in this particular case, we have negative, and this guy is also negative, and this delta S is positive, and our T is obviously going to be a positive number. That means that we will end up with a negative value for delta G at any temperature. So the temperature here is not that important. And we are going to have a spontaneous reaction at any temperature because no matter what you do, it will be a negative delta G. Now, if we go to the box on the bottom there, we have a delta H that is positive. We have a delta S that is negative. So with that delta S that's negative, it will turn our back portion there into a positive number, and it's not going to matter what temperature you're at in this situation. You're always going to end up with a positive value for delta G. And that means that this reaction is going to be pretty much non-spontaneous at any temperature that you put in there. So in this case, it's really our delta S that sort of determines what's going to happen here. And obviously here we got our negative that's going to change it out. Lastly, if we go to sort of the bottom box here, we have a exothermic delta H. We have a negative delta S. That negative, once again, is going to turn the back part into a positive number. This guy, though, is already bigger because he's in kilojoules. So that means at low temperatures, this reaction should be spontaneous. If you then get a really high temperature here, this positive part can overtake the front part and it will become non-spontaneous. So if we have, again, a negative and negative for delta H and delta S, at our low temperatures, we're going to get spontaneity, and at our high temperatures, we'll get non-spontaneous. Any questions on that there? So let's take a look at this here. We have this reaction, decomposition reaction, forming a little calcium oxide and some carbon dioxide. We have a delta H for this reaction at 177.8 kilojoules and a delta S at 160.5. At 25 degrees, why don't you calculate delta G and determine, is it spontaneous? So take a moment or two and calculate that up. Okay, so let's take a look. Obviously, in this case, as we've been talking about, they did give us a delta H and a delta S. So it would definitely make sense to use the equation that's got both of those in it. That would seem good. So again, don't reinvent the wheel or go calculate delta H and delta S again yourself or anything crazy like that. So in this case here, we're going to put our numbers in, and we will go with our delta G is going to equal 177.8. I'm going to multiply it by 1,000, and the reason I'm doing that, I'm going to turn it into joules. That way, again, everybody's in the same unit. I'm going to then subtract it by my temperature here, which would be 298 Kelvin, right? It does need to be converted to Kelvin. And our delta S there, 160.5. And that is going to get us 7.8 times 1,000 minus 298 times 160.5. And give us about a 129,971 joules, or 130 kilojoules if I convert it to kilojoules there. First off, any question on the calculation? Is this reaction spontaneous at 25 degrees? This reaction is not spontaneous. It's non-spontaneous here, as we have a delta G that has a positive value, and it would be as non-spontaneous. Now, in this particular case, could we actually figure out when this reaction would become spontaneous? And the answer is, yeah, we could do that. We know that for this reaction to become spontaneous, our delta G needs to be negative, and negative's on the other side of zero, I think. Yeah, so if you set delta G equal to 0, delta H minus T delta S, bring in the back end there to the other side, T delta S equals our delta H. And lastly here, I'll go right here, T is equal to delta H divided by delta S in this case. So, and again, we're just dividing that to the other side. Putting in our numbers in this case, 177.8. Once again, I'm going to multiply by 1,000 so I don't have any unit issues here. That's going to turn it into joules, 160.5 joules per Kelvin. That is going to get me a value for my temperature here of go with 1108 Kelvin. If I subtract that 273 from it to turn it back into Celsius, that is an 835 degrees Celsius. Yeah, it feels warm. First off, any question on that? Yeah.
Is the original problem, why did you use 290 Kelvin?
Because it was at 25 degrees. So we need to convert to Kelvin, and that was the temperature. Other questions? What does that temperature represent, and who knows, but what does that temperature represent? Yeah, it represents really the minimum temperature required for this reaction basically to turn spontaneous. So that is the minimum temperature that's needed for this reaction to turn spontaneous. That is a fairly high temperature, which we would expect based on our conversation a minute ago, where we have a positive delta H and a positive delta S. The only way the back part here can overtake the front part is at a really high temperature, and I say that would probably qualify as a pretty high temperature in that particular case. Now, if you look at the graph, that's what we see here. This is the pressure of CO2, and we can see right there at 835, we actually get some pressure happening, right? Now, you may say, don't we get pressure before that? And the answer is yes, but it's at 835 that we hit 1 atmosphere. And 1 atmosphere is standard pressure, right? So that's where we get to that kind of standard pressure in this particular situation. Obviously, before that, since there is only one gas in this reaction produced on the product side, we basically have a flat line. So we have no pressure, and it kind of means we have no gas, and that means we're not making any products until we get around that 835 point. Any questions on that? So this equation is useful. Obviously, you can use, as we just did there, to figure out is the reaction spontaneous under those conditions. And you could also use it to try to figure out in certain situations at what temperature this reaction could turn spontaneous, as we see here. Any questions? All right, so let's give this one a go. For the final reaction, our reactants or product favored at equilibrium under standard conditions here. Delta S, and we're looking about spontaneity really, or products or reactants sort of favored. Again, we're going to use our equation there. And here we'll plug it in. I am again going to multiply by 1,000 just to put my everything in my case here in joules. If you want to convert the other one to kilojoules, you can do that too. We're at 25 degrees still, so that's going to be at 298 on the temperature. And our delta S there is a negative 216.4 joules per Kelvin per mole. And popping all those numbers in, maybe minus 1204 times 1,000 minus 298 times negative 216.4. Get that out there. That's going to get me like negative 1139512.8 joules. Good sick, big sick. And we'll divide by 1,000 there, and maybe we'll do a little rounding here, negative 1140 kilojoules. Yeah, I think that means that this reaction is reactants or products are favored in this case? Should be products in this case, as it is a negative value for delta G. That means its reaction is spontaneous. It should head thermodynamically in that direction towards our products. Yeah. Question about that. All right. Let's talk a little bit about Gibbs free energy and phase changes. So earlier we talked a little bit about phase changes, and remember that when we do a phase change, we don't change the temperature, but we do obviously change the phase of a substance. And these things typically occur at the normal, for example, melting point, freezing point as we go from solid to liquid, and also the normal boiling point as we go from liquid to gas. And at exactly those sort of boiling points or melting, freezing points, we do have both phases in equilibrium with each other. And because of that, our delta G here will equal 0 because it's an equilibrium sort of condition. We can then rearrange our equation here and solve for the delta S. And this delta S would be the delta S of, for example, vaporization. And this is the equation here that I was talking about earlier that you do not want to mess up, which is we have our delta S is equal to our delta H divided by T. This is derived from this equation. That looks exactly like the delta S of the surroundings, except there's a negative in that one, right? Over that. You do not want to get these two confused. People always, when they're doing this one, wants to put the negative in there because they remember the negative here. So negative only on delta S of the surroundings. If you're doing something like this, like a phase change or something of this nature, that's derived really from this equation, no negative that's in there. So that's again a common sort of error that occurs. So if we look at this process here, this is water going from the liquid phase to the gas phase. And for water, that's 100 degrees Celsius, right? The normal boiling point where that occurs. And if we put in our values for that, this is the delta H of vaporization for water. That's the energy required to change water from liquid water, for example, to steam at 100 degrees Celsius, not change the temperature. And this is our boiling point temperature. 100 plus 273 gives us 373 Kelvin. And if we do all that good stuff here, we will end up with a delta S of what is known as vaporization of 109 joules per Kelvin. That does make sense in this case because we're going from a more ordered state, right, to a more disordered state, and we would expect the delta S here to be a positive value. Now, if we were doing, say, the opposite transition where we're taking steam and we're going to take it back to liquid water at 100 degrees Celsius, what is the only thing that changes in this calculation? The delta H would actually be a negative number, right? Because that's an exothermic process that would occur. That's 40.79 kilojoules divided by still our 373 Kelvin. Going to give us a negative 109 joules per Kelvin. The delta S of condensation, perhaps, yes, as what that is known as. That also makes sense in that direction as we're going from gas molecules, right, back to liquid molecules. So we're going from, again, a more disordered system to a more ordered system in the liquid state. So we could do this for vaporization and condensation. We could also do this at the transition of solid to liquid or liquid back to solid. A reminder, that's the delta H of fusion that is used to do that. For water, that's like 6.02 kilojoules per mole is the heat of fusion for water, basically. And it would be the same idea if you were going from solid to liquid. That's an endothermic process. Energy has to be put in. The delta H would be a positive number. And if you had a liquid to solid transition, that is an exothermic process. The delta H of fusion would be negative. Any questions on that there? So why don't you try one here? The enthalpy of vaporization for mercury is 58.5 kilojoules per mole. The normal boiling point is 630. What is the entropy of vaporization of mercury? Should imply going from liquid to gas, right? That's evaporation or vaporization that's happening. As you can also see here, and as you hopefully know, the delta H of vaporization, for example, for water is just for water, is different values for different substances. So as you can see here, for our mercury, we got something like 58.5 kilojoules per mole. We also, for different substances, have a different, say, boiling point, right? And this is 630 instead of 373 there for water. So this is our delta G is equal to our delta H minus T delta S. This is at equilibrium, right? As we're doing a phase change basically here, that means our delta G will equal 0. This is how we again get to our rearrangement here. We're going to bring that to the other side. T delta S is equal to delta H. Delta S would equal our delta H divided by our T. Once again, no negative here in this case. Putting it in our numbers in this case, I am going to go 58.5. I am once again going to times it by 1,000 because I just feel like it. And we're going to do our temperature here, which is already in Kelvin. The reason I did that is truthfully because delta S is usually given in joules, so why not do it? And it makes it a nice bigger number, perhaps. That's going to give us 630. So that's like a 92.9 joules in this case. Once again, we did hit for our delta S of vaporization a positive value, which would mean we're increasing the amount of disorder, which again would make sense in this case since we're going to the gas phase. And obviously, if we were doing, say, the entropy of condensation, the only thing again would change would be the top number would be negative. And that would again turn our delta S into a negative because again, we're creating more order in that case. Any questions on that there? Well, we haven't talked about equilibrium in a while. I feel like we should. Probably because the title says that. That's probably why I feel that way. All right. So we don't have enough delta G equations. So let's talk about a few more, just in case you're missing a few more options for delta G. So we have this equation here, which is the delta G equals the delta G naught. For good measure, there's 2 delta G's in there, plus RT natural log of Q. So what is the difference between the delta G's? Well, I'm going to go with one has a naught and one doesn't, pretty much in this case. So remember that, you know, those guys with the little knot on top usually mean sort of standard conditions, and that's usually table type conditions. So that's basically 1 molar if you're dealing with anything with concentrations. That's 1 atmosphere or 1 bar if you're dealing with anything with pressure. Again, sometimes people will wrap 25 degrees in there, even though technically not really, but 25 degrees is typically the temperature you find in most tables that you look up. So that's basically, you can think of it as delta G under sort of standard conditions. This delta G with no knot, you could think of non-standard conditions, basically. So basically something is not under standard conditions. 2 likely culprits is the pressures are not all 1 atmosphere, or the molarity is not all 1 molar. So that is how you know that's sort of the difference. R here is our gas constant, is actually the one with the energy version, the 8.314 version. Don't use the ideal gas law. That's a lot more conversion to do there. That is T, which is our temperature in Kelvin. And dare a throwback to old times there. That is Q. That is the reaction quotient, which, as you surely will tell me, Q is calculated the same as K. If it's calculated the same as K. So Q is calculated the same as K. So again, Q would be our products over our reactants. Yeah, just like you would calculate K. So this obviously in terms of choices for delta G equations, this would be your go-to in a non-standard condition. Yeah, so you got some pressures given to you or some concentrations that aren't 1. That's probably the equation that you need to do. Now, in some problems, this delta G is given to you, and in some problems it is not. So this delta G, if you need to calculate it, is the delta G of your products minus the delta G of your reactant. So you would go to the table, look it up and calculate it. Again, sometimes they'll give it to you and sometimes they won't, but that is again where you would get it is from the table and take products minus reactants. Now, if we do hit equilibrium, we have a couple of things that happens to that top equation. Our delta G equals 0, and then obviously we're at equilibrium, so K is involved. And substituting and rearranging this equation, delta G is equal to minus RT natural log of K. So as you could probably imagine, if there's any mention of equilibrium or equilibrium constant, that would be your equation to go with, I would imagine. So that is probably the one to use. Now, people all the time for the top equation there always want to subtract here, but it is a plus. So keep that in mind as well. People all the time always want to subtract. And then people all the time want to forget the negative here. So just remember that. The good news is you can kind of get the second one from this one. So maybe if you remember that one, you'll get the negative right in the second one if you know how to derive it. So there it is. That's a 4-pack of delta G equations. Yeah, so we got delta G with our H's and S's, right? So we can use that equation. We got delta G if we have just a reaction. Look it up in the table, products minus reactants. We have delta G under non-standard conditions, top equation there. And we have delta G that has anything to do with equilibrium constant, bottom equation, yes. Again, that's what I said earlier. Probably the best piece of advice is to just kind of choose the one that kind of goes with the information given to you in the problem is probably the best approach. Any questions on that there? Now, the good news about sort of that graph is it's just like really way too late to look at something like that. That looks crazy. But this is the extent of the reaction. And basically the idea here is when we have equilibrium, everybody wants to get to equilibrium. So when we have Q is greater than K, you could think of it like a ball, if you will. That ball is going to roll, come up the hill, and then come back, right? And it's going to want to settle there at equilibrium. That's the idea of what's going on here. So very odd, most often it's going to try to get there from that position, but also if you're greater, it's also going to want to roll back down the hill, right, to that lower part. Same idea here. More products, we're going to kind of roll down the hill and eventually kind of settle there at equilibrium. So that's the idea of what's going on there. The good news on these this formula here is we can also make predictions on what's going to happen. But because it has the equilibrium constant at this point, I would hope you know something about it and that you can still use what you do know, which is hopefully when you have a large value of K, that means you should mainly have products, right? And the only way to get the products would mean probably your delta G needs to be negative, right? So if you got a large value of K, that should end up with a negative value for delta G, which would mean products would be favored. If you had a small value of K, that would mean you would mainly have reactants. And the only one to kind of say over there on the reactant side is a non-spontaneous reaction. And that would probably be what would occur in that case. Obviously, if you're equal to 0, you got a heads or tails there, but nothing too big. And you'll be near sort of equilibrium. All right, so let's do some calculations, shall we? Calculate the equilibrium constant Kp for the reaction at 25 degrees. All right, so I see equilibrium and constant. I see some delta G, so I'm gonna pick the one that has all those things in it, and that should be this guy. In this case, we're not really given too much other than the temperature, which obviously we need to convert to Kelvin, so that's at 298. We could calculate the delta G in this case by taking our delta G of our products minus the delta G of our reactants. So in this particular case, we have 3 times the delta G value there for O2, which is 0. minus 2 times the value there that we have for O3, which is 163.4 kilojoules. That's going to give us a delta G for this reaction of negative 326.8 kilojoules. Yeah. At this point, we now have our delta G, we have our T, and R is a constant, right? That is our 8.314 joules per Kelvin per mole. Well, I guess we're ready to do it here, I suppose. Let's put our numbers in. We're gonna go negative 326.8. Once again, I'm gonna multiply it by 1,000 to get it to joules. The main reason is R is in joules. So again, you do not want differences in units here. Otherwise, you're going to be in some trouble. That's going to give me negative my 8.314 joules per Kelvin per mole. My 298 there. Erase this. I got somewhere to write that there. All right, 298 Kelvin and my natural log of K in this case. All right, so basically gonna take all this and, bring it that way there, divide it over. So negative 326.6.8 times 1,000 divided by, I go negative 8.314. That brings my negative to the other side, and divided by 298. That's going to get me a natural log of K is equal to 131.9. To get rid of the natural log, we're going to E both sides there. When you do that, that just goes away. And here we will end up with, go with 1.9 times 10 to the 57 in this case. Yeah. Question on that calculation. Does our numbers make sense? Is this reaction spontaneous? I'm going to say yes, because there's a negative delta G. That means we should make some products, right? And we should have a large value of K. And I would say that sort of constitutes pretty large value of K in that case. So again, these things should agree. If you got a small value of K, you probably did something incorrect. Do you have a question?
Yes, I want to know why you put 0 kg in for the.
That is the, if you went to a delta G table, that would be the value you would find for O2. Yeah, so delta H of formation and delta G of formation. Anything on the table, if you go look it up, that's sort of in its standard state, not attached to anything, just by itself, like are things that are found like O2, N2, H2, all those guys will have values of 0, basically. The only one where you'll find values for things like that is like we saw with delta S. When you go to the table, you'll find some values for that. So sometimes they might not even give you those values and just assume that you know that they're kind of 0. So if you kind of like, if it's something that's not combined, then, it should be 0 as long as it's not delta S. Other questions? All right, continuing on here, has K in it. In this case, actually, we have the K. We have our temperature that, again, we need to convert into Kelvin, gives us 298. And R is a constant, so we have that guy always available to us. So we basically got everything on the right-hand side here, so plug it in there and see. Negative 8.314 joules per Kelvin per mole, which is our R. Our temperature here, 298 Kelvin. Our natural log of 1.7 times 10 to the minus 6. All right, let's see here. Let's do the natural log of 1.7 to the negative 6, then multiply it by 298, then multiply it by 8.314. Don't forget there is a negative as well. And that's going to give us a delta G here of 32,914. These are actually in joules, or approximately, that would be 32.9 kilojoules in this case. Is this reaction spontaneous? This reaction is not spontaneous. Reactants would be favored in this case. And we also know that because our KSP is a small value, which means we're gonna hang out over here, right, on the reactant side. And again, both of these values agree with each other, right? We got a positive and a small value of K. Any questions on that there? All right, dare I say one last one to finish it up. Delta G naught for the following reaction is 2.6 kilojoules per mole. In one experiment, only one experiment, the initial pressure of the H2 was 4.26 atmospheres. Of the I2 was 0.024 atmospheres. And the HI was 0.23 atmospheres. What is the delta G for this reaction? And which way will this reaction head? Reactants, products? No way, just take a vacation. All right, calculate it up, see what you come up with. Okay, so let's take a look. We're looking for delta G here, and we're going to go with our delta G is equal to our delta G naught, which we are also given here. And that would be the only equation that has both of those in there, plus an RT natural log of Q in this case. Once again, remember it is a plus there, not a minus. So this is where we use our non-standard conditions. And what is non-standard conditions here? It is actually the pressures. Remember that standard pressure is 1 atmosphere. So because these pressures are not all 1 atmosphere, this would be under non-standard conditions. And that's what makes it basically non-standard conditions. So we are looking for this guy. They were nice enough to give us this value. And again, if they didn't, you would need to go to the table there and do your products minus reactants and obviously calculate that. So under standard conditions, is this reaction spontaneous? Say positive 2.6. No, right? So under standard conditions, reactants are really favored in this case, right? It is a spontaneous reaction. All right, so we have R, which we always have, which is our 8.314 joules per Kelvin per mole. Somewhere there's a temperature. There it is, 25 degrees. So that's going to give us a 298 Kelvin. We do need to calculate Q in this case. And once again, Q is calculated the same way as we do K. So that's going to be our products over our reactants. We are dealing with pressure. So in this case, it would be the partial pressure squared of HI divided by the partial pressure of H2 times the partial pressure of I2 in this case. Putting in our values in the correct location, I think 0.23, and we want to square it, divided by 4.26 and 0.024. That's going to give us a Q value here of 0.23 squared divided by 4.26 divided by 0.024. 0.51741, not too much rounding there. So now we have our Q. So we are really ready to go here. We're going to put into our equation here, delta G is equal to our delta G naught, 2.6 times 1,000 to convert it to joules. Again, I want to do that because R is in joules, so we do not get any issues with units here. Plus my R, which is in joules for me. Again, you could convert R into kilojoules if you want as well. What else we got there? Temperature 298 Kelvin, kind of curving downward here. And our natural log of Q, which is 0.51741. All right, let's see what we end up with here. It's gonna natural log that number I got. I'm gonna times it by 298 and times it by 8.314. That's gonna get me somewhere here on the back end, negative 1632.5208-ish. And here we still have this guy. Times 1,000. So let's do that then, 2.6 times 1,000, and we're going to add it to what we had there. There it is. That is gonna be, I think, a delta G here of 967 joules in my case. Or 0.967 kilojoules, if you want. Question on that calculation there. Is which direction is it going to head? Towards reactants or products? Yeah, it's gonna go towards reactants in this case, right? As we did end up with a positive value for delta G, and that would mean reactants would be favored in this case and basically non-spontaneous in this particular reaction. Any questions on that one there? All right, that wraps up chapter 16. That is the last chapter on your exam, which is next week, right? Which is covering chapters 7, 16, 20, 92, 45, chapter 106, just to be safe, right? Now, so obviously, chapter 7 and 16, right? We're quizzing up on chapter 7 this week, which was asked for. No, I'm not pointing to that, not by you, you weren't asked for. But you did say you like chapter 7, so we're gonna quiz on chapter 7. Should be a nice, easy quiz, hopefully, at the beginning, and then we'll get into some electrochemistry. Any questions on that there? All right, today is back to experiment 9. You were all prepared last week with experiment 9, and now you're gonna go and tell me we left it at home today, right? I hope not. All right, so we're gonna do known today. Yeah, a little unknown on Thursday. Sounds like a plan.